Well, what we want to say a few words about today are greenhouse heating, which is sometimes called global warming or climate change. But the end message I want to give is one of Christian hope and Christian responsibility. There's no need to have doom and gloom about the situation of the climate. And as I'm here from the Compass class, no Compass class lesson is complete without poetry. How many of you know this spiritual? Okay, so anyway, there's you know the story of Noah and the rainbow promise. And how many of you know this poem by Robert Frost? We have Jenna in our class who is from New York, and it's a lovely poem about fire and ice. Same message as the either will suffice. The earth is always at risk. You know, Thornton Wilder wrote a book, The Skin of Our Teeth, about the ice age coming. So, you know, we take for granted our comfort, but there's always possibility of climate change that we have to adapt to. Of course, Adam and Eve had to force with a big change of climate. And somehow ever since, we have tried to get back there. It's been in our subconscious. We have this yearning, this feeling that the world should be a beautiful, perfect place. And yet somehow it isn't. You know, the sin where we mess it up. Okay, well, one of the obstacles to understanding climate change often is a too literal reading of the King James or some other modern translation of the Bible. But if you look at what Bible scholars tell us, what did God really tell us to do about the earth when he commanded Adam and Eve and all of humanity to take care of the earth? Did he say subdue it, crush it? There are 4 Hebrew words that are used in the story of Genesis where God gives man the mandate, and man and woman and humanity the mandate to take charge of the earth. The first 2, Rada and Kabash, and you may know the Yiddish and Irish, put the kibosh on him. That means to control and subdue. The first 2 words are not often used in the whole of the Old Testament. Only about 20 times for the first one, a few less for the second one. So the second 2 words are much more, hundreds of times they're used throughout the Old Testament. And they mean to work, serve, or till, and that's where God gave man the responsibility to work the Garden of Eden, to till the Garden of Eden, and take responsibility for it. And the word for the responsibility there is shamar, which means keep or watch or preserve wherever it's used in the Old Testament. So the idea that the environment is out there for us just to exploit and use or misuse however we want, and God will take care of us, is not biblical and is not faithful. In fact, the Judaic tradition has a tradition of trying to restore, to heal creation after we've fallen from that ideal situation of the Garden of Eden. So what's going on nowadays? Up until a couple of hundred years ago, man was so insignificant that no matter what we did, it wouldn't much affect creation. We just didn't have that much power. But what has happened, particularly in the last 100 years, is technology has given humanity the power to really alter things. We can go out into space, but we can also alter our environment here. Not to brag, but I gave a paper at the 3rd Jerusalem Conference on Information Technology in 1976 where I spoke about this. And since then, it's become a commonplace that we are producing so much energy, so much material, so big a population that we are altering the very environment of the earth. And geoscientists call this the Anthropocene. It's an era that is where the fundamental equilibrium of the earth has changed due to the effect of humanity. The Anthropocene, the age of man. Like the age of the dinosaurs, the age of coal, carboniferous, whatever. But we're in the Anthropocene, and I'll show you why. I want to keep in mind, though, that what we're, as faithful Christians, we will save the earth if we obey God. If we believe and obey the Bible, We will save the earth, its people, and its environment simply by practicing good stewardship as we're commanded, and as Jesus advised us to. It's just good housekeeping, for one thing. Okay, we're going to have a little light hiatus here now, having introduced all this serious theology and thing. Let's have a little break of our common mindset, because what we really need to do is break out of our mindset. We're stuck in a rut, particularly in this country. Not so much in China, Africa, Australia, but in this country, we just take certain things for granted. So let's think about, what if we treated everything, we had to have oil and gasoline and internal combustion for everything. Okay. How would things be different? Okay. Okay, now, we got a good video camera back there. And what about going to the dentist? Okay. Or toys, electric toys, wind-up toys for that matter. Oh, but we've got gasoline in the kitchen to refill if it runs out. That's okay. To understand climate change, we have to really understand energy. Energy can be confusing. It's so fundamental. Energy is the most basic thing in the universe. Empty space is full of energy. Energy can neither be created nor destroyed. It always has to be conserved in some form. Matter is a form of energy. Light, heat, motion are all involved with energy. So, and most of us know that, but then there's another important distinction. When we use energy to do work, and what technology has done is it's enabled us to move beyond our ability to harness just animal energy and simple plant energy, and we can now unleash huge amounts of energy from all kinds of sources, and we're doing that. Traditionally in the 19th century, starting in the 18th century, we started using coal and fossil fuel oil, and then in the 20th we used nuclear and natural gas more, and we were able to expand the Earth's population many-fold. There are now more people alive than are dead, and have been now for a number of years, because of the exponential rise of human population. Well, in the 21st century, a new appreciation has come for forms of renewable energy, and we're going to talk about the difference between non-renewable and renewable. One of the byproducts of non-renewable energy is waste heat. Another is waste combustion products. And what do those waste combustion products do? By the way, if you have questions or comments, right, we'll interrupt here. Okay, go ahead. So, okay, everybody knows about the combustion. Notice everything over here depends on heat. Heat is a random motion of molecules. And they learned back in the 18th century, and even the ancient Greeks knew you could heat water up and make steam. It had power. You could use it to move things, whether it's a spinning top, like in a temple in Greece, or a water pump in a coal mine in Scotland, or a steamship, or a locomotive. That steam is powerful, and you had a whole age of the railroads and factories and everything powered by steam, the Titanic, and it was all powered by heat. And then toward the end of the 19th century, clever people learned to harness that heat inside a closed cylinder in an internal combustion engine. Now, they actually started trying to do this with gunpowder, but that didn't work very well. And but by the time that abundant oil became available, they used diesel fuel and then gasoline, which is even more explosive power concentrated into a small area. Well, you can get, there's a saying in science thermodynamics that science owes more to the steam engine than the steam engine owes to science. Because while engineers and practical people with an urgent need to mine and transport and travel were developing better and better steam engines, scientists were looking at what made this work, and the whole science of thermodynamics came about. And out of thermodynamics, statistical mechanics. And Einstein's first publication was in statistical mechanics, actually, and the photoelectric effect and the Brownian motion. But it can be shown, fundamentally proven, that the maximum efficiency you can get by harnessing heat is about 23%, the thermodynamic heat limit. If you just use random motion and you take a difference between a hot object and a cold object, energy is always going to flow toward lower energy, and you can harness that flow in the form of steam or random motion of molecules and take that randomness and put it in a cylinder and convert it into one direction. And that's how you get energy or useful work out of steam or out of any other form of heat. You can also turn a turbine by having the motion push on blades, but you're still limited to about less than 0.25% efficiency. All the rest goes as waste heat. Now, what's happened with the rise of electricity is we can control things down at the nano level and the sub-nano level. We can use what was called in the 19th century a Maxwell's demon. Maxwell said, suppose you had a demon here watching all these random molecules, and it had a gate, and it could open the gate and let the energetic molecules through, and close the gate if a slower molecule came along. And very soon you could drive heat uphill instead of having it flow downhill, and you could heat things up without wasting wasting energy through the randomness of the whole process. But with electricity, you can come close to doing that. Moving electrons and moving atoms a few at a time, you can avoid the randomness and you can get much, much higher efficiency. I'll show you an example. Well, first of all, where does all the heat come from? All of our energy on Earth, with very small exceptions, comes from the sun. Even our petroleum, our coal, they are stored sunlight from many years ago. The sunlight is converted into carbon matter by plants. If the plants die and are buried under certain conditions, they convert into coal and into oil. And we then dig this oil up and burn it. We're basically borrowing sunlight from millions of years ago when we do that. Even when we build a wood fire in our fireplace, we're borrowing wood from previous summers to release the heat in this winter, because the tree has stored up that sunlight as wood, and then when we burn it, we release that sunlight energy back as heat. And notice every time that we store energy and then release it, it goes into a coarser, less dense form. The sunlight comes in as very high energy, which we know is visible light. It strikes the earth, and the earth absorbs it. Some of it gets reflected. The reflected light goes back out as regular white light, and the atmosphere is transparent to that, so only a portion is captured and stays on the earth. Well, what if all the sunlight that hits the earth stayed on the earth? What would happen? Well, we know what happens on the moon. On the sunny side of the moon, what's the temperature? Okay, on the dark side of the moon, what's the temperature? See, our atmosphere moderates our environment. It keeps only a portion of the sunlight on the earth, and it lets the rest dissipate. It distributes the heat from the sunlight all around the earth, so we have a moderate climate. That's one of the marvels of creation, if you like. The earth is just right for us. But what happens when the sunlight hits plants and earth and soil? It's absorbed, and then some of it stays as heat energy. It's lost as light. It no longer can be light, but it then radiated out at a lower form of energy, which we call infrared radiation. Now, you know about infrared because you have a microwave at home, right? A microwave uses infrared and a little longer wavelength of light to heat things up. And so when visible light hits a blacktop pavement or a plant leaf, it's converted to heat. And then when it's re-radiated out, it goes out in a less concentrated form. And some of that goes right out into space. And so we're kept from overheating by the re-radiation of sunlight out into space in a different form, as well as just reflection in the same form. But now, some of that re-radiated heat, though, can be captured by certain parts of the atmosphere. Now, the sky looks blue to us, and Lord certain physicist in the 19th century got the Nobel Prize for figuring out why is the sky blue. Have you ever had a child ask you that question? Why is the sky blue? It's a difficult question to answer in scientific terms, but when they finally figured it out, the scattering, the red light and the infrared light get absorbed more than the blue light, which is higher energy. Now, only part of the atmosphere absorbs this heat light, and that's the biggest part of that is carbon dioxide. Carbon dioxide is a product of burning carbon fuels. Carbon combines with oxygen. The gas that goes off is carbon dioxide. And carbon dioxide absorbs infrared and keeps exchanging it with other molecules and then radiates some of it back down to Earth. So it acts like a pane of glass. What makes a greenhouse work? Have any of you actually have had a greenhouse? My cousin stayed at an English lord's house when he was stationed in the Air Force over there, and there were all these greenhouses up in this northern cold climate, and he's from Texas, and he restored them and replaced the glass, and soon he was growing tomatoes up there. Because visible light comes in through the transparent glass, it hits the soil and bricks in the greenhouse. If it's re-radiated, it goes out as infrared light. Well, the glass is not transparent to infrared, so the heat energy of the infrared gets trapped inside the greenhouse. That's why your car can get up to 150 degrees very fast if you park it out in the sun. The glass in the car windows lets the visible light in. The car starts to heat up, but the visible light has been converted to infrared heat light, and so it can't get out. So the car becomes an oven. If the sky were transparent to infrared, that wouldn't be a problem. If glass were transparent to infrared, then people in northern climates like England and the Netherlands, by the way, the Netherlands exports more food than almost any other country, and most of it's grown under glass. But Iceland has a similar thing, and except that they also have hot springs to help provide a source of heat. But this disparity between the visible light we see and this infrared light that we cannot see with our eyes, although we can feel the heat from it, is what makes the greenhouse effect. Now, in the 1870s, a physicist, chemist, back then there wasn't a lot of difference, everybody was a natural scientist, named Arrhenius, a Danish, Swedish, Scandinavian guy, started thinking about what happens to all the coal that we're burning now that we're in the industrial age, the Iron Age. And he sat down and figured it out. Well, most of it goes into the atmosphere as carbon dioxide. And infrared light had just been discovered, and it was found that carbon dioxide absorbed it. And he predicted that if we continued to burn coal at the rate we were doing in 1870 and kept increasing the rate, that we would warm the Earth because we would be creating a greenhouse cloud over the Earth of carbon dioxide. Unless, of course, the carbon dioxide was removed. Well, how does it get removed? Plants use it to make carbon materials, so it can be recycled. Without carbon dioxide, plants couldn't make sugars and starches and food, and they use light to energize that process. But at the rate we burn coal, we're outpacing the rate that plants can replace it, especially if we cut down forests and pave over prairies. But Arrhenius back then said, oh, look, we're going to warm the Earth because he calculated the rate of coal burning and other fuel burning and the rate of land clearing. And he predicted what the warmth of the Earth is. And he thought, this is a great thing because what they were really afraid of back then was a new ice age. And they really, there were signs that the Earth was cooling, and I'll show you some historic plots later. So they said, okay, this is good. We'll keep the Earth from having the oncoming ice age. And I mentioned earlier Thornton Wilder's By the Skin of Our Teeth about an ice age that comes and destroys civilization. Okay, but this is pretty complicated, but basically very simple. Visible light hits things, converted into heat. The heat mostly goes out, but if we have a lot of carbon dioxide, it's trapped and gets re-radiated back. If we have a lot of plants, they use up the carbon dioxide. There's other places the carbon dioxide can go. It dissolves in the oceans. and makes carbonate, and sea animals use carbonate to make hard shells, and little diatoms use carbonate to make their little shells, and some of them use silica as well. But so the ocean is absorbing some of this carbon dioxide. Plants are absorbing it. So up and over the long term, this all comes out in a nice, beautiful balance, amazingly. It comes into equilibrium. The balance of carbon dioxide production by burning and heating from the sun and cooling from radiation out into space, and fixing of carbon by plants and sea animals, and even when granite erodes from volcanic eruptions in mountains, that absorbs some carbon dioxide. Of course, a lot of other carbon dioxide is blown up into the air by the volcano itself. So there's a balance, but everything stayed in balance. But the sun shines every day. One of the most reliable things in the world. Everybody knows the sun's going to come up tomorrow. You can even know exactly what time it's going to come up and how long it's going to shine. So you can predict how much energy we're getting from the sun. You can't predict how much oil is going to be drilled 50 years from now, or how much coal, but you can predict how much energy we're going to get from the sun. And yet, the sun energy is not absolutely constant. In this period of the sun's evolution, the sun is gradually warming up. So in about 3 billion years, the Earth's oceans will all boil dry, and the Earth will be too hot to have it, but that's a long time away. But in the closer time, the sun varies. When there's sunspots on the surface of the sun, it's more active, we get more heat, a very tiny, tiny percentage of a bit more heat. But on things the scale of the Earth, that can make a difference. But there's another way that the Earth's climate can vary, and that's simply because of the Earth's orbit. We call that winter and summer where we are, because we tilt away from the sun in the winter, we tilt toward it in the summer. But there are other effects, very subtle effects, that clever Russian mathematicians and astronomers worked out in the 19th century. That because the Earth is like a top, it sort of precesses. There are actually times when it's slightly further away from the sun for hundreds of years, thousands of years, before it comes back into a more circular orbit. And those times actually correspond to ice ages or very warm periods, depending on the circulation. Now, people who don't like to say that man can influence the climate say, oh, we're just in another one of these Mikhailov cycles. The Earth's just being perturbed, and it's a natural thing. Well, let's look at the history of them. Here, those are 400,000 years, 500,000 years, 600,000 years, 700,000 years. And these are records of the Earth's climate that we can get very accurately from isotope ratios of ice cores and sediments. And you can see there have been periods when the Earth has been very warm and periods when it's been very cold, and those cold periods correspond to ice ages. And that green line is also a record of the carbon dioxide in the atmosphere. And the climate scientists call there are two effects that force climate. They force it hotter, they force it colder. Carbon dioxide forces it hotter. The solar effect can force it cooler or hotter, depending on the cycle we're in. Well, see, these cycles take place over 100,000 years or so. They're very slow and gradual. And look where we are. Okay, we go down to 0, because on this scale, you couldn't see much. So we've expanded this scale out, much bigger here. So you can see what's been happening recently. And recently, we've departed from the normal Milankovitch cycle. We're just going up, up, up. First of all, we're going up, up, up in carbon dioxide, the green line, and we're going up a little less in the temperature. And why aren't we just following the carbon dioxide up straight with the temperature? Well, because temperature is not the same thing as heat, and I'll explain that in a minute. But is there any doubt that we're no longer in a normal cycle? We have departed from it. We're in the Anthropocene age. We have influenced the climate. Okay, maybe something else influenced the climate? Well, not many other candidates possible. Okay? Here's what's happened since records have been kept, starting about the time that Arrhenius predicted warming, and people started keeping detailed records. This is both southern and northern hemisphere. You see, climate is very variable. Some comedians say, if the climate's warming, how come it's snowing? So out there. Or that's like saying, I was recently at a conference where somebody had a slide of the Titanic, and the back part of the ship is going way up, and they say, oh, we're not sinking, we just rose 50 feet. So, so you can say we go up and down, but if you take the long trend, it was pretty level, and when people were afraid we were going to have an ice age, and in fact, due to the Mikhailovich cycles, we were due to have an ice age. But we intervened in that, and instead of an ice age, we started warming up, coinciding with the rapid technological industrialization and increased use of oil and coal, and increased concentrations of carbon dioxide, and increased deforestation. Okay, so that's all doom and gloom, right? Well, let's look at, here's what's happened way up on top of one of the highest mountains out in the middle of the Pacific Ocean, where there's no industrialization around to speak of. They measure the carbon dioxide. And by the time it diffuses out there, it should be the average for the whole world. So this observatory on the top of Mauna Loa in Hawaii measures the carbon dioxide. And see, since they started in 2013, the carbon dioxide just keeps going up. Now, why does it go down? What are those downward ones? That's summer, when the plants are taking it out. It goes up in the winter when the plants go dormant, and we heat more, we burn more fuel to heat. And this is northern hemisphere. You could do the same for the southern hemisphere. So there's cycles. All the plants take carbon dioxide out of the atmosphere, and then we pump it back in. The plants take it out, we pump it back in. But are we winning or are the plants winning? Okay. There's your trend. Okay. Now, some people have said, and very well-funded people, said, oh, the climate has stopped warming. There's a hiatus in global warming. Okay, here's your hiatus right here. You see it's sort of leveled off. Or has it? Well, there have been hiatuses. If you look at the big trend, there's no hiatus. It's a blip. We're going up and up and up. It took 20,000 years for the Earth to warm up a few degrees centigrade. Now, that was a catastrophe. 80% of all sea life died because the ocean got too acidic to support shell formation. Most of the land plants and animals died because the climate got so hot and deserts spread. And so it was a 20,000, by the time it ramped up to 4 or 5 degrees, it was a mass extinction. It took 200,000 years for the Earth to cool back down and plant and animal life to diversify again. Okay, and the rate at which that warming occurred was 0.025 degrees centigrade per 100 years. Now we are warming at the current trend between 1 and 4 degrees per 100 years. Okay, so are we going to be able to adapt to that? Are plants going to be able to adapt? Is the ocean going to be able to adapt? Well, we have a chance if we keep it to 1 or 2. If we let it get out of control and go to 4, then we'll be in trouble. And serious people are trying to keep it from going to 4. We still have a chance to do that. And why is that? Okay, well, first of all, how do we know? Anybody still doubt that we're warming? You can go on a lot of blogs, and although 99% of all climate science publications say we're warming, and a recent study out at Texas Tech showed that almost every one of the studies that claim that we're not warming had serious flaws in it or even outright misrepresentations. There's one way that you can measure the warming of the Earth, and that's because ice melts when it is worked on by heat. The random motion of molecules, heat, will raise temperature, but it will also melt ice. So what's happening to ice around the world? Well, this is what's happening to the Arctic ice cap. And the Antarctic, it's not quite as clear. I have a slide later if you want to see it, but it's dramatic what's happening in the Arctic. Okay, my wife Cindy says, well, who says? Where does that come from? Okay, these sneaky scientists or, and look here, the worst of it is only projections. This is what's happened up to now. So how else, if we don't want to trust meteorological data that's been collected, how else can we do it? We can look at the Earth through satellites, which we've been doing for a few years. And here's where the ice used to be, the average winter extent of Arctic ice, and here's where it is now. Actually, here's where it is 2 years ago. It's even less now. So ice is melting in our half of the world anyway. Ice, and there's what it looks like in the winter, summer, winter. And here's the record, again, the opposite of the global warming trend is the ice melting trend. It's falling down. Again, you have the summer, winter, summer, winter. A lot of variation year to year. But on the whole, we're losing the ice. Why does that matter? I mean, you can be sentimental about polar bears and penguins and narwhals. Well, much of the world depends on ice for its water. South America is now in a water crisis. Peru, Ecuador, Bolivia are running out of water in their cities and in their agricultural operations because the glaciers have disappeared. The lakes are going dry. The hydroelectric dams that we built for them with foreign aid now don't work because there's not enough water melting off the glaciers. Because the rate at which the glaciers build up in the winter from snow is not meeting the rate at which they are melting. The same thing's happening in the Andes. Oh, in the Andes, the same thing that is happening in the Andes is happening to some extent in Asia, all over the Middle East. That's one reason you have so many refugees. And a lot of the wars are water wars. The big lakes in Central Asia are drying up. Lakes in Africa are drying up. Glaciers that stored water in the winter and then released them over the summer where they were available for drinking and agriculture are disappearing. And some glaciers are growing, and you always get the people who want to take the other side. Oh, this glacier grew. Well, if you look at the whole thing, 90% of them shrink, 10% grew. One reason glaciers might grow is as the oceans heat up, more water boils off, and there's more water vapor available to make snow in the winter. So you can have really big snowstorms, but all that water melts very quickly and creates erosion if you have then a hot summer and a longer, hotter summer. And this is one of our glaciers in the U.S. You can go there and see them, and the Glacier National Park has very few glaciers now. So unless you're sentimental about the narwhal or the polar bears or all this wonderful, beautiful ecosystem, then who cares? It might be an opportunity. You can develop all this frozen land. You can drill for oil. You can make farms in Siberia, plant orange trees in Siberia. The Russians actually tried to do that back in the 30s. But, so this is a painting made in the 19th century from an expedition that tried to go across the Arctic. This is an icebreaker in the 1960s that managed to make it through most of the way. Very heavy-duty icebreaker. Actually, the first people that were able to sail across the Arctic were in a nuclear submarine going under the ice, as you may remember. But now, in 1969, a special icebreaker tanker was built. Any of you old enough to remember that? We were running an oil crisis, and gosh, if we could just bring Alaskan oil across the northern territory. So we'll build this huge, the largest ship ever to fly the U.S. flag, this tanker, the SS Manhattan. Specially built reinforced hull, very strong engines. It was an icebreaker, but it was also an oil tanker. And it was going to start carrying oil across the north to the refineries in New Jersey and even down to Houston. Well, it didn't make it. Got frozen in, ice penetrated the hull. It had to pull in at Baffin Bay, and so that whole project was abandoned. There was just too much ice. It was too cold in 1969. So do you think that we ever give up? No. This year, the Russians sent a tanker. It's not even an icebreaker. It wasn't even escorted by an icebreaker. It's just a regular old tanker, and it sailed right across without any trouble. You think I'm exaggerating? It must have had a lot of trouble going through all that ice, right? Well, you can book a passage on a cruise ship this year, and they actually have already completed one cruise across the Northwest Passage. Not an icebreaker cruiser, it's a regular cruise ship. You can sit in your cabin and photograph the polar bears as you break up their ice, and bring back some pictures. Okay, so what's the real importance of ice? Well, first of all, is there any doubt that the ice is disappearing? You're going to still have people writing letters to the Wall Street Journal saying it's not. But it is disappearing. Nobody really doubts it. Now, water is an amazing substance. Life would be impossible without water for so many reasons. But one of the reasons is that when heat, random motion of molecules, you can see up here, when the visible light or infrared light starts heating up things, it can do one of two things. It can raise the temperature, which means the molecules move faster, or you can have a kind of a Maxwell's demon. If the molecules that are moved faster bump into these solidly bound molecules and break them up, that does work. And energy has to be conserved so that heat is transformed into work and the temperature stays the same. So as long as we have ice on the Earth, the temperature will be moderated. The ice will absorb that heat. In absorbing that heat, it melts and makes more water, but there's no more heat. The water stays at the equilibrium temperature near the melting point of ice. However, once you use up all the ice, then there's nothing else for the heat to do but increase the temperature. So that's what happens when you get a real departure from the norm and you get a global warming phase. No more ice to moderate it. All that happens is the temperature keeps going up and up and up, and it's a vicious cycle. Because when the temperature goes up so much that the plants die, then it really takes off even more, and so on. And hopefully we're far away from actually boiling the oceans, but that's where it all leads. And notice here, how long this phase lasts depends on how much ice you have. The more ice you have, the longer the phase can be, and we have a lot of ice, so we still have a lot of time. You can prove this in your kitchen. This is if you put a thermometer in some ice and water, that will stay at 0 degrees until all the ice melts. Then it will start to heat up. As long as there's ice for the heat to do work on, you won't heat it up. That's called thermodynamics. Okay. It's very well, it's been known for 200 years. Okay. However, there's other problems if all the ice on the Earth melts. For one thing, all that water that's melted has to go somewhere. So here's what the U.S. would look like if all the ice melts. And it doesn't look much different if only half of it melts. And this doesn't even take into account the fact that water expands when it's heated. Right now, a significant part of the rise in sea level, which is well documented, is not from the melting ice, but from the expansion of water, just like the mercury in a thermometer expands, or water in your water thermometer with the red dye expands as the temperature goes up. The oceans expand when they're heated, and they're expanding because they're heating. Now, a lot of this heat is being taken out at the poles as the ice melts, but it takes a while for it to flow up there. So the oceans are heating a bit and expanding, and so the sea level is rising. And in addition, the ice is melting, so the sea level's rising. And in addition, there's another greenhouse gas that never gets mentioned. It's not chlorofluorohydrocarbons, it's not methane, it's water. Water comes from hydrocarbons. What's the hydro in hydrocarbons? We burn hydrocarbons as our gasoline. Hydro is hydrogen. So when we burn coal, which is mostly just carbon, we get mostly carbon dioxide. When we burn gasoline, we get half carbon dioxide and half water because the hydrogen gets oxidized by the oxygen, and that makes water plus carbon dioxide. So every time we burn petroleum fuels or natural gas, we're producing water that was down under the earth in a non-water form out into the atmosphere, and it again has to go somewhere. So we're producing more water into the Earth's environment. In fact, natural gas, because it's carbon with 4 hydrogens, produces twice as much water as carbon dioxide per unit amount burned. But that's a little side thing. Also, there's a lot of political resistance to the truth. What does this say here? When I went to research this, places I used to go for data, suddenly the page is gone. What is happening here? I don't know. I'm not even going to comment on it. You can go investigate yourself, okay? But I managed, there's still a lot of data around. Okay, now, why am I optimistic? Why am I not up here saying, go and, get ready to meet your maker? Because we can change things so easily. It's just like falling out of a log. Okay, back in the 80s, I remember how many times I read, you can't conserve your way to prosperity. You can't save your way to prosperity. You got to use more energy. Energy conservation is a waste of time. What Carter tried to do with energy conservation is just useless. Well, what has happened since 1980 in our national energy use? And this is just in the U.S. Or is it? Yeah, this is the U.S. Gross domestic product has risen 149%. Contrary to all projections made at the time, energy use has not followed gross national product use. Okay, it has stayed level, and yet the economy has grown. Okay, part of that is because we're using renewable energy, and renewable energy is just much more efficient. It follows the same kind of law as computer chips because it is silicon chips. So the cost, the more we make, the lower the cost gets. The lower the cost gets, the more they sell. So it's taking off just like computers. Solar energy is taking off. Even no matter what estimates you use, whether rooftops or total global solar, it's taking off. And all we need is a different mindset. If we just abandon inefficient, outmoded ways of doing things and go to more efficient ways, see 92% efficiency, and that's the standard, National Electrical Manufacturing Association. 98% efficiency versus 20% efficiency. So we got a lot of room to avoid carbon dioxide altogether. We can produce electricity from many different ways that don't involve carbon dioxide and don't involve other byproducts and costs, and don't take a lot of electricity and fuel just to produce the product that we burn, namely gasoline, and then don't have to transport it. And instead of burning the gasoline, we can use it to make very useful things, pharmaceuticals, fertilizers, all kind of things that are really very valuable. So that's why Exxon is investing most of its investment into petrochemicals, not into fuels. The same with the Saudis. Because for one thing, they're more profitable than just burning it. People used to burn amber for fuel. Nobody does that now. And we lose, in big central generating plants, we lose most of the energy anyway, transmitting it, converting it from AC to DC. So if we really want to make America great and avoid global warming and create jobs, here is a study in Massachusetts at Harvard and MIT. How many jobs are produced from natural gas per $1 million investment versus how many that are produced by biomass or solar or more efficient transportation? So that's, where have the jobs gone? Maybe we're just stuck. If we just give up our, if we hung on to old technology in communications the way we hold on to it in energy, this is where we'd be. And in the meantime, the rest of the world is not standing around. Do we see these around us? Why can't we export things to China? Because China wants to import the most efficient energy technologies. They don't want to import more oil or gas or gasoline-burning cars. They've already outlawed gasoline-burning cars in their city, and so has India. And even entrepreneurs in Africa are selling these little solar panels very cheap, so everybody can have lights, they can have telephone, they can have everything in their village, they can charge their cell phones. So I'm optimistic. Things are going to get better, much better. And I have hope for the future, provided we just listen to what the Bible says. Thank you. Okay. Thank you.